Let's take a look at BlueDentist in action. The BlueDentist hardware is capable of running standalone for data recording or connected to an HDMI display for active monitoring. Here, you can see the typical output of an extended monitoring session. The highlighted lower address parts are iPhones that we set up intentionally for testing. These have a lower address part of BB, 5B, F3, and 8D10AD. Additionally, a Bluetooth device with the LAP of 890F5E was also detected. This was not a targeted device and was simply active in the environment.
All right, well, let's get started then. Hi, everybody. We're BlueDentist, and we're excited to share with you all our Capstone 2020 project. With the explosion of connected electronic devices, wireless security efforts are in high demand. BlueDentist targets Bluetooth devices, which are traditionally hard to track due to their unadvertised presence and frequency hopping. BlueDentist utilizes a software-defined radio to collect data from a large band of frequencies in conjunction with an NVIDIA Jetson Xavier to efficiently process the large stream of data in order to provide a user interface which details all local Bluetooth devices and activity. An expandable storage interface allows for long durations to be monitored unsupervised. I'm Jeff, and I primarily worked on the hardware design of the project. In particular, I worked on integrating the NVIDIA Jetson into our design, the high-speed design and layout, and the STM32 microcontroller firmware.
Hi, I'm Chris Chan. I also worked on hardware design and was responsible for microcontroller integration, power management design, and Jetson adaptation.
I'm Griffin Danninger, and I work to develop the BlueDentist software focusing on the configuration of our SDR and CUDA drivers, optimizing our algorithm, and conducting final testing.
And I'm Zach Battles. I also worked on the BlueDentist software, focusing on the multi-thread building, the algorithm design for our program, and the open source code library integration into our project.
Bluetooth monitoring presents a unique challenge because devices only announce their presence when establishing connections. After this, connections begin frequency hopping between 79 Bluetooth channels. However, transmissions from a unique master device using traditional Bluetooth are uniquely identifiable due to their stable access addresses. Existing Bluetooth SDR solutions, such as the Ubertooth One, have the bandwidth to cover only a single Bluetooth channel at a time. This makes them great for communicating over Bluetooth, but a poor choice for monitoring. BlueDentist records data across all Bluetooth channels. When set up in a Bluetooth-rich environment, this enables our program to identify multiple unique master devices by their access address active at the same time, and record their data transmissions over a prolonged period. This could be useful to identify specific offending devices in a secure room that is supposed to be radio silent, or recognize malicious Bluetooth interference activity out in the world.
The project was split into two independent halves, with Jeff and I working on the hardware platform and Griffin and Zach working on the software. Since we are attempting to catch and analyze Bluetooth signals that are operating in the gigahertz range, our hardware needed to be fairly advanced to keep up. The key components of our design are a powerful NVIDIA Jetson Xavier to do the data processing, specialized XTRX software-defined radios communicating via PCI Express, NVMe SSDs for fast data storage, and full I/O for a native Linux system including HDMI, USB, and Ethernet. To support all our components that total around 65 watts of power consumption, specialized power design was needed. We also included a STM32 microcontroller to handle I/O expansion and board-level control for the sensitive power-up sequencing. Jeff will go into detail on our PCB design process.
To deal with the complexity of our design, we created the schematic in a hierarchical layout. The image shown here is our top-level design. You can see the several core blocks to our design in this image: the Jetson, power supply, and STM32 microcontroller. There are additional blocks for peripherals, such as the connectors for the radio, SSD, USB, Ethernet, and HDMI. The connections on this schematic carry groups of connections between the relevant green blocks here. Some of the connections even carry up to 10 signals. Each green block in this image is actually its own separate schematic page. For example, this is a schematic page for the STM32 microcontroller I/O. Each design block, those green blocks on the last page, on our top level schematic contains a separate schematic page of similar complexity. But designing the hardware schematic wasn't even half the battle. The layout turned out to be extremely challenging. Given the Jetson, radio, and SSD, our board size came out to around 7 inches by 7 inches. A 699 pad BGA connector is used as the interconnect between the Jetson and our board. Additionally, the majority of the high-speed connections in this design are concentrated in one section of the BGA connector, which you can see around the center of this image. This required us to use 8 layers in order to break out all of the required signals while preserving signal integrity. These high-speed traces, such as PCIe, Ethernet, HDMI, and USB 3.0, had really strict routing requirements. We had to learn how to use tools to calculate trace width and spacing to maintain the target trace impedance. And to achieve realizable geometry, we needed to consult with our board house in order to create a custom board stack-up. Not only did we need to maintain controlled impedance, but many of the high-speed nets also required matched lengths, both within differential pairs as well as pair-to-pair.
In addition to the density and high-speed signal requirements, our board design also came with complicated power requirements. Our board contains 6 different power rails, with some designed to handle 10 amps continuously. Each rail also includes control circuitry and discharge circuitry to ensure correct sequencing on power up and power down. Since we are using sensitive components, we also included reverse voltage protection, EMI filtering, ESD protection, and automatic power failure control. This power design also had to account for thermals and proper current distribution. We also made sure to minimize interference with the high-speed signals from the power circuitry. Our power design also made considerations for hardware development by including manual override controls for all rails for careful board bring-up. This feature proved useful when we were programming and testing our board before connecting the Jetson module. So this is a view of our fully fabricated and assembled PCB with the Jetson Xavier module plugged in. Not visible is the SSD located underneath the Jetson and the XTRX radios which reside on the bottom side of the board. A big complication for us was that the 699 pin connector the Jetson Xavier uses to interface with our board was out of stock everywhere. We ended up having to resort to transplanting an existing connector on one of our dev kit boards with a heavy amount of rework involved. Both we and the board assembly house had to rework the connector to even get connection on the BGA pads. To check for shorts and breaks, we painstakingly continuity tested all important pins before we tested our board firmware.
Unfortunately, the connector was just fatally damaged, and we didn't have any success with this board due to warping on the connector from all the rework. But miraculously, we were actually able to source the connector just 1 week ago. We spent the entire last week bringing up our board with a new connector. Just when we were about to give up hope, everything just started working. We were so overjoyed when we got video out of the Jetson on our custom board. We took some quick benchmarks and we observed a 1 gigabyte per second read speed on the SSD. Overall, this was the most complex board Chris and I have ever worked on. But now Zach and Griffin will detail the software side of BlueDentist.
So to start, for the software, we'll look at this flowchart that shows how our program essentially works. ISM24 is the name of our master program that creates and controls the 4 threads of our program on the CPU and is in charge of the display. ISM24 refers to the 2.4 gigahertz band that we are watching where Bluetooth operates. First, we have the capture thread, which sets up the XTRX radio parameters such as gain, tuning frequency, and sampling rate. It then captures packets within the ISM24 band and passes those packets on to our analysis thread, which calculates the channel power and sends this information along with the packet to the noise estimation thread. In our noise estimation thread, we receive 250 samples, and we use these samples and their power levels to calculate a noise floor for each of the Bluetooth channels we are monitoring. If a packet passes the noise floor, then it is determined to be interesting, and we pass it to our decode thread. In this decode thread, we are able to find Bluetooth access codes from the received interesting packets from the noise estimation thread. If the packet we are looking at is in fact a Bluetooth packet, then we will find its access code here. I will discuss the process for finding the access code in more detail later. When we are collecting data, we are monitoring the 2.4 gigahertz band for bursts of activity. We centered our program at 2.425 gigahertz. In the waterfall plot to the right, you can see a 1 megahertz bandwidth signal that is above the noise floor. This is an example of a signal that we would decide to process and try to find an access code for. Now, the way that our Bluetooth decoding works is first we separate a captured frame into 1 megahertz channels for us to process. We then take these channelized frames and demodulate the channels to get the actual data out of the radio signal. Next, we run each signal through a frequency modulated squelch, which acts as a noise gate to suppress weak signals so that we do not waste time processing them. The resulting signal is then run through an algorithm that extracts the LAP or the access code from the signal using a code word and syndrome as a means of decoding. All these processes are done on the GPU. With the optimizations we made using CUDA, we were able to improve the run time by a factor of 10. And with these optimizations, we were able to analyze each Bluetooth channel in parallel and decode Bluetooth access codes in real time.
To present this information to the user, BlueDentist uses a command line interface program. After establishing the noise floor, the program logs each lower address part, the channel it was found on, and the file in which the data is stored. Because LAPs are static, the program can also be configured to highlight targeted devices. Now we have a quick video demo so you can see it in action.
Let's take a look at BlueDentist in action. The BlueDentist hardware is capable of running standalone for data recording or connected to an HDMI display for active monitoring. Here you can see the typical output of an extended monitoring session. The highlighted lower address parts are iPhones that we set up intentionally for testing. These have a lower address part of BB5B F3 and 8D10AD. Additionally, a Bluetooth device with the LAP of 890F5E was also detected. This was not a targeted device and was simply active in the environment.
To best parallelize our hardware and software development, we made use of the Jetson Xavier development kit and XTRX PCIe connector, allowing us to closely simulate the final hardware being designed by Jeff and Chris. Throughout the software development process, we faced a number of challenges beyond just the algorithm design. One of the major roadblocks we overcame was debugging and repairing the XTRX and SOAP SDR drivers. We also used multi-threading to optimize our CPU processing and heavily parallelized channelization and decoding with CUDA on the GPU so that we could achieve live processing. The XTRX SDR also required extensive testing to properly tune parameters for noise floor estimation so that BlueDentist can be useful in any environment.
To best summarize our project, we achieved our primary goals. We completed our BlueDentist hardware, integrated the XTRX radio, NVIDIA Jetson Xavier, and STM32 microcontroller. We also developed software to scan, collect, and analyze RF data to display Bluetooth activity in real time. And perhaps most importantly, we received the commendation of our amazing sponsor. I'd like to personally thank Rory McCarthy for making this project possible with CACI's sponsorship. I'd also like to thank James Cook and Dwayne Gardner for being a huge help during the design process. We literally couldn't have done it without them. Lastly, I'd like to thank Professor Yoga, Adi, and Kyle for mentoring us throughout the Capstone project. Thank you all.